Hi, I'm Mateo. I'm an electrical engineer, and I'm the project manager and financial officer for this team.
Hi, I'm Patrick Fiske. I'm also an electrical engineer. I'm the safety coordinator and the test engineer for this project.
Hey, I'm Allardi, and I'm the logistics manager and manufacturing engineer.
Hey, you're probably wondering who our client is. Our client's SecurShade. SecurShade is headed by Clements and Iain Portalupi.
You're also probably wondering what problem we're trying to solve. This problem is that during emergency situations, the time it takes to close the shades in a school is way too long.
And why should you care about this problem? 1, because it makes teachers and students feel safer in the classroom, and 2, because it could save lives.
Our first customer requirement is small size. Our second one is easy to use. Our third one is comfortable to hold. And our last one is low maintenance.
There were a number of factors we had to consider when designing the remote. The first thing we had to consider was whether to use an external or internal lanyard mount. In the first iteration of the remote, we used an external lanyard mount. However, in the next 4 iterations of the remote, this was changed because we didn't want to have extruded material outside the size of the remote, as it increased the length and increased the volume of the remote, which is one of our main specifications we were trying to minimize. Another change we made to our design was the change from a 2-button system to a 1-button system. The reason that this was done is because we didn't want teachers to accidentally hit the wrong button in an emergency situation. The next thing we had to consider was the geometries of each remote. In the first iteration, we used a rectangular profile. In the second iteration, we used a pod-shaped profile. In the remaining 3 iterations and in the final design, we used a curve-shaped profile that was meant to match the curvature of the fingers when the remote is held in hand. In the first iteration of the remote, the PCB laid flat inside of the remote. In the second iteration of the remote, the PCB laid on an elevated platform with screws to hold it in place. In the final iteration of the remote, the PCB lays on a mounted surface with alignment tabs to hold the PCB in place. This was chosen because it doesn't require additional screws to hold the PCB in place, but it does still provide excellent battery clearance. Additionally, the PCB in the node was mounted the same way as it was in the final iteration of the remote.
For the electrical portion of this project, there are a number of things to be considered when designing. One of the first things was looking back at the old remote that was given at the start of the project. It has 2 buttons. As said before, we switched this to 1 button. Some other choices that we made in this design were switching from AAA batteries to LiPo batteries. There are a few reasons for this. One of them is that the AAA batteries were way too big. The LiPo battery fits nice and easy inside of the remote casing. The second reason is the LiPo batteries are rechargeable, which saves on waste and maintenance for the user. For the node portion of the electrical design, one of the main design options we had to consider was between using a DC to DC converter and a logic level switching MOSFET and the previous design of 2 voltage regulators and 2 MOSFETs. The reason that we went with a DC to DC converter and 1 MOSFET was that we ended up choosing a logic level switching MOSFET that can be driven directly by the microcontroller. This saves down on components and space on the board. For the DC to DC converter, this was chosen because of the high efficiency output that it has. Another design option that we made involved uploading the code. Originally, we had 6 pins that come out of the PCB right here. The problem with this is that it had design constraints when it came to size of the board. It added extra space coming out. To solve this, we ended up spending slightly more money on a tag connect. The main reason that we chose tag connect was for mass implementation. In the previous design, if you had the 6 headers, every time you wanted to upload the code, you would have to directly wire 6 pins to that. Now it's super quick and easy to just put the device on the board and upload the code immediately.
There were a number of measures taken to ensure a sustainable mechanical design. The remote and node were both designed to be as small as possible, therefore using as little plastic as possible. Additionally, both the node and the remote are designed in individual components so that if something breaks, the single piece can be replaced rather than the whole remote or node.
The first thing we designed for is size. In our design, we sought to make the PCBs as small as possible in order to reduce the waste in fabrication. Additionally, we chose a rechargeable lithium polymer battery. This was a change from the previous design, which used 2 AAA batteries. We revised the remote and reduced the number of components while keeping the same functionality and increasing the efficiency.
There are several trade-offs made throughout this project. One of the main ones was trading off the battery size versus the battery life of the remote. One of the main things our group wanted was to have the remote last throughout a whole school week. but at the same time, we also didn't want the battery to be so big that it made the remote big and uncomfortable to hold.
One of the mechanical trade-offs we had to consider was whether to use a pod-shaped geometry or a curved geometry. The pod-shaped geometry allows for more battery clearance, however the curved geometry allows for a smaller remote profile.
Overall, the design choices we made and the trade-offs we considered are what made our project what it is today.
One of the technical analyses that I did on this project was using the failure modes of analysis software on SolidWorks to simulate forcing on the remote. This software allowed me to visualize the internal stresses on the remote with different loading situations, such as the remote being dropped by a teacher. In my simulation, I used nylon as the material, as that's likely the next step in the evolution of our design.
One of the technical methods that we used within our project was the use of KiCad. KiCad is a software that allows you to model your circuit and then change it into a board view. Within the board view, you can route traces between the electrical components in order to match it to your schematic. There are many intricacies that you have to consider when using KiCad, a few of which are via setup and layer setup. In our design, we used 4 layers, 2 of which are designated to the ground and power plane. When doing 4 layers, the amount of traces in the design can become ridiculously large. In order to reduce this, by adding a power plane and a ground plane in the middle, you can connect vias right next to the pins in order to reduce the number of traces moving throughout the circuit.
Both the volume and weight specification for the remote have been reached. The current volume of the remote is 3.076 cubic inches, and the weight of the remote is 0.08 pounds. Additionally, the node is also within the volume specification at 11.87 cubic inches.
Currently, the battery recharge time is 1.25 hours, and the battery life is 4 days.
The mechanical portion of this project was successful and completed fully. The electrical portion of this project is not fully completed at this point. All of the functionality has been demonstrated on breadboards and the PCBs have been developed. There are slight issues with the PCBs which are delaying testing that prevents us from fully completing our project. We believe that once these issues are addressed, both of the boards will be fully functional.
The recommended actions for continuation of this project include creating a user manual for the product, diagnosing the issues with the PCB shorting, and addressing methods of manufacturing with increased production volume.